In section 9.2, we're going to identify the mathematical relationships between the various properties of gases, and then we're going to use the ideal gas law and related gas laws to compute the values of various gas properties under specific conditions. So there are a lot of different types of gases. These can be single elements like noble gases like argon or helium. They could be a diatomic element like hydrogen, nitrogen, or oxygen, or they could even be compounds like CO2, carbon monoxide, water, or ammonia. All gases, though, have the same dependence on four properties: volume, the amount, which we'll describe as N, usually the number of moles, the temperature T, and the pressure P. The pressure of a gas is directly proportional to its temperature in Kelvin. At a constant volume and a number of moles, P is going to equal KT. This means that they have a directly proportional relationship when we write it this way. This is known as Manton's law or Gay-Lussac's law. And we can picture what that means here. So when we cool down the gas, it's going to have a low pressure. We heat it a little bit, it gets to a higher pressure, and then when it's very, very hot, you're going to have even a higher pressure. So as we increase the temperature, we also increase the pressure. If we graph that out, we're going to see that as a straight line, a linear relationship between pressure and temperature. The volume of a gas is directly proportional to its temperature in Kelvin as well. At a constant pressure and number of moles, the volume is going to equal some constant times the temperature. This is Charles's law. And again, if we graph that, we're going to see a straight linear relationship between the volume and the temperature. The volume of the gas, though, is not directly proportional, but inversely proportional to its pressure. So at a constant temperature and number of moles, we're going to have that the pressure is going to equal some constant divided by the volume. This is known as Boyle's law, and if we graph it out, we're going to see that there is this curved rational function, 1 over x function that you may have learned about in your math courses. If we, however, wanted it to be a line, we could always graph either 1 over p here or 1 over v here, and that's going to make it look like an actual proper straight line. The change in volume is actually how you breathe. So when you push down on your diaphragm, your lungs expand. This causes an area of low pressure. Air flows in, then you contract it, create higher pressure in your lungs, and push it out. The volume of a gas is directly proportional to the amount of gas. So if we hold the temperature and pressure constant, we have that the volume is equal to, again, some constant times N. This is known as Avogadro's law. If we look at these four relationships and we want to combine them together, the simplest way that we can do that is something called the ideal gas law. And it's PV equals nRT. So pressure times volume is going to equal the number of moles times R times the temperature, where R is a constant that is an amalgamation of all of those other constants in these other formulas up here. R has a value. It is 0.08206 liters times atmospheres per mole Kelvin. You can look up R on Wikipedia and see that it can have many other units. So depending on your calculation, you may want to use a different one, like say have bars instead of atmospheres or kilopascals or something like that. So what is the ideal gas law? The ideal gas law accurately describes the properties of an ideal gas, a hypothetical construct. So ideal gases are not ones made of atoms or molecules that take up any space, and they do not interact with any other matter. So we're going to assume that the things that make up the gas don't take up any they don't have any volume themselves, and they're not going to interact with themselves or anything around them. No gases are ideal, but under certain conditions, we can assume ideal behavior. What are those conditions? The gas must be at a low pressure. They should have a high temperature, and these conditions combined together are going to result in a dilute gas comprised of fast-moving molecules. And if you think about it, that kind of makes sense that we can assume that they're not going to interact with each other when they're moving really fast and they're nowhere near one another. Also, if it's very dilute, there's not a lot of gas in there, then the volume of the actual gas particles is going to be pretty small in relationship to the container, and you could assume that it would approach zero. Sometimes it's important to define standard conditions. So standard temperature and pressure is something you'll see a lot, STP. And this is defined as 0 degrees Celsius and 1 atmosphere. You should note that IUPAC recommended value of standard pressure was changed to 1 bar in 1982, but many texts continue to use the 1 atmosphere value. At STP, the volume of 1 mole of ideal gas is 22.4 liters. So we can picture that here where we have all of these balloons. They're all under standard conditions. They all are exactly 22.4 liters, but each one contains a different mass of atoms because each one of the atoms weighs a different amount.